So it's important that we do prospective environmental assessments at the city scale to look at what would these different technologies and the systems change our emissions and sustainability before we have large-scale adoption. So we know where to build the infrastructure. How should we incentivize the right people to use the right thing? Okay. So out of the three things, we have done some research in all of them and different combinations of them. So today I'm going to mainly focus on the shared mobility part. Towards the end, I will share with you a little bit some of the other aspects. And for shared mobility, I'm going to start with, how do we get information to look at what's the current emission impacts of the system, and also how do we build models to inform the future development. So for shared mobility, it includes shared micro-mobility, which is bike share, shared e-scooters, which you can see have a big increase in recent years, and also vehicle sharing and ride pooling. You can see all three figures we have upper increasing trend. But the question is shared mobility equals to sustainable mobility? So the way we actually evaluate these systems is by looking at their life cycle emission impacts. So what is life cycle environmental assessment? Having a bike share system, a bike doesn't have tailpipe emission, but it doesn't mean it's zero emission. We actually need to look at, the manufacturing of the bikes. If it's a station-based, the manufacturing of the docks, what kind of material goes into building the docks? Is that steel? Is that iron? Right, plastic? We also have PV panels. We may also have a battery goes into the control panel as well. Right, if it's a dockless bike share, we need to consider they need electronics to remotely, wirelessly unlock and lock the bikes, right? Some cell phone use, and that's the manufacturing phase. And for the use phase, after we ride the bike to somewhere, we drop the bike, right? It may not be the places where other people want to pick up the drop bike. So there's a process called rebalancing to move the bikes from where they have been dropped off to the places where there could be potential demands, right? This rebalancing is actually mainly done by vehicles, which will have emission as well. And we also have end of life treatment of the bikes. So this shows the bike graveyard in China when we have a lot of the floating bikes being launched and then failed in many of the cities. So taking all of these into account for transportation modes, for each mode, we actually have something called emission factor. Basically, from a life cycle perspective, to travel 1 passenger miles or 1 passenger kilometer, how much emission is associated with this mode. So actually done the first environmental assessment for bike share to establish this emission factor. It's for a representative system. And then there's also some variation in terms of across different cities and the system size. So from this figure, you can see a couple things, right? This is station-based, this is dockless. On average, the dockless is much higher than the station-based, but but with the variation, it could also be same or the other way around. And for station-based, the orange one is rebalancing. It's a big part in both of them. And then the other major part is the infrastructure, the docks and the stations. For dockless system, rebalancing is the major thing because the bikes are very distributed. It needs a lot of time, efforts to collect them and then redistribute them. So how does that compare to other transportation modes? So we take the shared e-scooter data from another paper and then average private vehicle, bus, personal bikes. So you can see the shared bikes are here. And if we look at the bus, right, it could be higher even than the average bus for a dockless bike share system if it's not very well managed. And then if we look at private vehicle, right, really the emission reduction potential comes from replacing car trips by using the bike. Now, again, this is a representative system, right? System to system, there's a lot of difference. And in this study, we also made some assumptions. For example, for station-based bike share system, we assume that the stations are powered by the PV panel equipped at the station. But if we look into the details, let's see if I can play the video. Yeah, okay. So this is Chicago. We all know Chicago is well known for its architecture. And a lot of these bike share systems are actually deployed in downtown area, which have those tall buildings. So the shadow from the buildings and the nearby, trees actually block the sunlight from those PV panels. So we evaluated really, for the bike share system, their PV panel, depending on their different locations, how much solar radiation they can receive and how much electricity they can generate compared to how much electricity each station would need based on their usage. We actually find out a lot of the stations cannot be energy self-sufficient, which means, if the battery is depleted, the station cannot function. To make the station function, in addition of the bike rebalancing trips, you actually need additional battery replacing trips, right, to operate the system. So that will actually increase the emission factors for the station system, almost double this rebalancing part, right, which bring it a little bit further up towards to the bus emission factor. So again, replacing car trip is really the important thing if we want to reduce carbon emission through shared mobility, shared micro mobility. So, but are we really doing that? So we want to look into that for bike shared bike use. What trips are they replacing? So here we focus on the station-based bikes because they are still the majority use in terms of trips in the US. Yeah. So in the literature, how people analyze this is mainly from two approach. One is based on very simple assumption, right? Longer trip beyond 1 mile would replace car trip. Okay. Or people would do a survey asking if bike share is not available, what mode would you use? And if we have, X% of user reported they will be replacing car, what they would do is to use the total trip distance from bike share system, multiply by the emission factor, and also the percentage of that claim they would replace a car. Right? There's a couple issues here. So number one, percentage of user doesn't equal to percentage of miles, because some people are more heavy users. Some people may only use it once, right? And also for the same person, I may use it to replace car in the morning when I'm in a hurry, right? I may use it to replace walking when I'm in a hurry, but in the evening, I may use it to replace car when I have more time, right? For the same user, it's also different. So we want to take a different approach. We want to take a data-driven approach. Looking at each bike trip, what's their potential to replace trips with different modes? So how do we do that? We want to look into their spatial temporal patterns. So for each bike trip, we use the transit network data and the schedule data to look at, okay, is there a bus station nearby? Okay, is there a bus coming soon? Right? If the person needs to wait for a long time or have 5 transfers to make the same trip, they're not going to use public transit, right? Is this a feasible trip to use bus? Okay. If it's not feasible, then the probability of replacing transit will be set to 0. And then we also look at what are the historical travel pattern people would do in terms of travel distance and different mode split, right? You can see here Blue is the walking, so shorter distance, there's higher probability to walk, but even at very short distance, there's still a lot of car trips, right? For a longer trip, there's more transit and the car as well. So we would look at how long is the trip, what's the likelihood people would choose different modes as well. And we also have this probability by different time of the day. And also based on urban area and the suburban area as well. So we looked into a case study of 8 systems in the US, ranging from smaller ones, like the Seattle and the Los Angeles ones, and also larger ones, the Chicago and New York City ones with more than 500, 600 stations. And the results shows that if we look at total, so number one, yes, there's carbon emission reduction potential from bike share system. But how big the potential is depending on how big the system is, right? If we look at the total emission reduction, the larger the system is, there's more total emission reduction. But if we look at the efficiency by per mile traveled, the blue bar, or by per trip, the orange bar, we can see that actually there's a cutoff in terms of about 5-mile system diameter. If we have a too small a system, the potential is too limited, right? If the system needs to be at about 5 miles to have a higher efficiency in terms of reducing the carbon emissions. And spatially, in the downtown area, the total emission will be high. So the bigger the circle is, the larger the number. But if we look at per trip, right, the downtown area, because the trips are very short, right? So it's very hard for them to replace car. Okay, so the emission reduction potential will be lower, but the suburban area further away actually have higher potential to reduce more carbon emissions. So it tells us if we want to reduce carbon emission, we actually need to move the bikes to, out of the downtown area. Okay. So that's for bikes. Okay. How about scooters? Okay. Yes.
I have a question.
Mhm.
Have you thought about it in the inverse sense, as in if you have a better system for like bike sharing, for example, it might convince more people to use a bike versus just walking, and then it would increase emissions?
Yes, we will get to that later. So we have a model that built to exactly answer that question.
Okay.
So now in this analysis, we also have a strong assumption that we're looking at a trip to trip comparison in terms of what substitute what, right? But there's also a potential that originally it could be a car trip. Now I use shared bike shared scooters to serve my first or last mile of both, and with some public transit in the middle, that will enable me to replace a longer car trip. Okay. So we also want to look into this issue, and specifically we switched to e-scooters because of its higher usage in Indianapolis. And so specifically for a case study of Indianapolis, we look at, okay, is e-scooters competing or supplementing the local bus system? So for Indianapolis, the bus system is actually designed in a way that they all goes to downtown. So all the lines here is different bus lines, and you can see they all goes to the downtown. Okay. And then the red color here shows the daily e-scooter trips. So the darker the red is, there's more scooter trip. Again, you will see more trips in the downtown area, but there are also some along the bus line as well. So we looked at 1 year of e-scooter data. We used the daily bus schedule and the bus ridership, and looked at similar approach in terms of comparing its spatial temporal relationship with the bus schedule to see is it very short trip, very far from the bus lines. It's unlikely that the bus is competing with the scooter is competing with the bus, right? It's possible that the scooter is actually providing complementary service when the bus is not running or the bus is not covering that area. If it's a trip that we can actually take a bus to finish, right? Which means a shorter walk to the bus stop, right? Not a lot of transfers, and the trip makes sense. we then consider it as a potential competing trip. Again, it's potential, it's possible to have the substitution, right? Whether is indeed there a competition, we will confirm later. All right, so the results shows that about half, 44% of the trip has no impact on the bus system, which means they're likely just replacing walking, right? And then we have about the same split between competing and also complementary. But if we look at the complementary, so this is cross out the day, what percentage of the different trips, okay? Most of the complementary trips are the orange, these ones are when the bus is not available or not in the region, right? Out of the service time, the region that doesn't have a bus route covering, right? It's more from the spatial temporal perspective complementing. For the last mile, first mile connection, the share is very, very limited. Not a lot of a first and last mile connection based on the current use. And then if we look at where are the competing relationships, so this figure shows that if it's more blue, it means the region has more competing trips. If it's more red, the region would have a higher complementary relationship. So not surprised at all, the downtown region is mostly competing, right? In some of the area, for example, IUPUI area, right? We have more of the complementary relationship that we can observe. So now again, the previous data only shows there's a possibility for the substitution, but is it really happening? We need to confirm that. So we did a DID model, difference in difference model, using the bus ridership data to look at the regions where we have a scooter usage versus the region that don't have scooter usage, and how does the bus ridership change over time, okay? If we can confirm that in the region, in the treatment group, where we do have scooters, there's a further more decline of the bus ridership, then we can confirm that there is a competition relationship. And then we actually did confirm that there is a competing relationship in the regions with e-scooters. So indeed, it's competing with bus. So now, what does that mean? What should we do, right? One thing to keep in mind is the data we have is observe the demand, right? As you mentioned, when you put the bikes or scooters at different places, the usage could be different. Or when you put more bikes or scooters, the usage could be different. So we looked at where would the operators rebalance the scooters, right? You can see a lot of them goes into the downtown area where the relationship would be competing and that you would have low carbon emission reduction opportunities. Right. So we really needed to distribute the bikes and scooters in the suburban area complementary relationship regions. But how do we do that? Right. We needed to have either regulations or incentives for the operators to put the bikes and the scooters there, and also potentially we need a better integration in terms of management and the payment system between these shared micromobility and public transit, which is not trivial at all. All right, oops. Okay. So based on what we have learned about the current system, we also noticed some issues, okay? So issue number one is the historical trips are only observe the demand, okay? We also want to know how do we improve the system? Now, when we improve the system, how does the demand going to change? How do we model that? And then also is this complex relationship between the different modes, right? Here we also only look at, okay, bike versus traditional modes, right? E-scooters versus traditional modes. But actually, they're also competing against each other. right? Bikes and the scooters are also competing against each other, right? We also have those first mile, last mile, multimodal trips, right? All these different modes are potential options. They're all competing from the same pie. So the same model should have all the options in them to really understand this mode shift. Okay. So that's why we designed a model, what we call an agent-based integrated traditional and transformative transportation system use model to study this, to have all these components in the model to answer the question, how should we improve the system? And when we improve the system, how would the things change? So what we did is that it's an agent-based model. So our agents are households, individual travelers, vehicles, scooters, all of them are agents. So we use the American Household Community Survey. So information about the households, information about their survey pattern, information about their travel pattern, existing transportation infrastructure, road infrastructure, bus schedule, right? Land use pattern to generate the household and individual agents. And then we conducted a mode choice survey to study how would people make their decision given different situation. And then we then used the current shared model, shared mobility infrastructure system as the benchmark, and then we can study different future development scenarios based on the model output. We can then know how would the people shift from one mode to another. How does that translate into vehicle miles traveled in terms of emissions, equity, etc. Yeah. Right. Any questions so far? So how do we do that? For the agent-based model, we have a new approach of generating travel demands. So what we generate is an linked agents between households, travel people, and their trips. So we actually generated households. We know the household's property, their income level, right? How many people are in there? How many adults? How many kids? What are their age, right? Education level, who has a driver license, etc. Okay. So for a household with, for example, 2 adults, 1 kid, right? We would then generate those travelers as adults and the kids, and then they would have, travel patterns assigned to these agents that is according to the travel patterns of the community. And then their trip chains, so they would, for example, travel from home to school, right, and then to another location and back, and someone else, the orange person may go to work, go to the same place and come back to pick up the kid and come back home together, right? Yes. And then the location of the trips will actually follow the land use pattern as well. For example, if it's a home-based trip, right, the home location of the households needs to be in a residential area, okay, not in a park, for example. Okay. So we actually generated a full synthetic population for the entire Indianapolis. So we know every single household. Of course, it's not true, right? But like aggregately, this whole population should have the statistical property of our Indianapolis residents. Right? But we have, hypothetical synthetic population for everybody. Right? And then we conducted a survey to ask them, how do you trade off time versus money in terms of commuting trips or non-commuting trip? So we have a survey with different scenarios. We would give them some choices in terms of, okay, you're going to lunch. So there's a story in the survey. Okay, so this is a lunch trip, right? You have 3 options. You could take the bus, you could take the scooter, take the bike, and which one would you choose, right? We have also asked them about, right now, how do you typically travel? And we would set their major travel mode as the benchmark to compare with the other modes. Okay, and then they would also be asked about, okay, how about commuting trip? They would answer a bunch of questions as well, right? So for the commuting trip, which is longer, they would have the option to use the multi-modal trip. For the lunch trip, it's a shorter trip, so it's more of a single model trip. We also collected social demographic information in terms of their income level, education level, so we can then match that to our agents. So after we collect that information, we use the integrated choice and the latent variable with a cross-nested legit model to build the mode choice utility function. So we use a cross-nested legit model because for some modes, for example, ride hailing, right? Some people may actually perceive it as a car-based travel, but some people may actually perceive it as a shared mobility travel, and then they would actually have different value in terms of preference. So we analyzed the data, generated the utility function for different households, right? And then we can, for each of the households we simulated, we then have an equation that we could use to calculate, okay, you have a trip from point A to point B, right? Looking at the nearby choices, right? Is there a scooter nearby? How long you will need to wait for Uber, for example, right? Is it how long you need to walk to a bus station? How long is the total trip? And they could calculate the utility of using different modes, and then they can pick what they would like to do. And we also included fleet operation in the model as well. As I mentioned, bike share needs to be rebalanced, right? Scooters needs to be rebalanced. So we have some built-in rebalancing optimization model inside. So after you use the system for a day, there's a vehicle will drive around to rebalance the system. So we capture the rebalancing emissions as well. And then for the Uber ride-hailing services, there could be dispatching, right? When the vehicle is idle, they may choose to drive to a different location, right? What we call dead heading, zero passenger trips, just to try to wait in the area that potentially have higher demand. So we want to capture those travel and emissions as well. So we also calibrated the model using the American household, the American community survey data in terms of, comparing, look at where we generated the residents, households, how does that compare to the current distribution? And in terms of mode share, right, from the National Household Travel Survey data versus our base scenario with no shared mobility, you can see it's quite comparable and may have a slightly higher walking trips, okay, but relatively comparable. Okay, so now with this model, we can then look at, okay, for our current shared mobility infrastructure and use, how much emission we are saving or increasing, and also how about future scenarios. Okay. So from the base scenario, which has no shared mobility, you can assume that to be maybe 15 years ago versus current scenario where we do have some scooters, some bikes in Indianapolis, some Uber rides. So majority of the trips are still car. You can see the Indianapolis is a very car dependent area. Right, we do have some walking shifted to e-scooters, right, consistent with what we observed in our previous analysis. Right, we also have some bus trips shifted, a little bit car, right, also of some trips shifted to ride-hailing as well. So emission-wise, compared to the base scenario, the current scenario actually has a higher emission in total. Okay. Mainly from those Uber ride-hailing, Uber Lyft trips because of the dead heading, right? Moving around when you're searching for your passengers, right? They're increasing the emissions. Although the bike share and the e-scooter help to reduce a little bit emission, right? But it's not as much as those increased by the ride-hailing service. So in total, the emission actually increased. It's not reducing. So what do we do? Okay, so now it's time to explore, new scenarios. So we started with 3 different scenarios. We looked at it. Scenario 1 is a density-based development. Okay, so within the area where we have current system, let's just put more bikes, more scooters, maybe encourage more people join the Uber service. Okay, or we can say we just want to keep the current system as is, but deploy more bikes and scooters kind of around in the outer side area. Or we can say, okay, the deployment should be along those bus lines to see if they can encourage more multimodal trips. So the results shows that if we intensify the system, we're actually going to shift a lot more of the walking to bike and e-scooter trips. Okay. There's still a lot of the car trips will stay as car trips. Okay. A lot of the bus trip will actually become, e-scooter and the e-bike trip, shared bike trip, right? Still, intensifying the system will not help, right? As we have already confirmed of our observation. So the problem is not, we are not having enough. Yeah.
Very quick questions.
Yes.
Is your model also considering weather?
Weather, no. That's a, yeah.
Like my intuition is northern parts of the US, it's like, at least in this weather, so you have considered 1-year data, like from August 2018 to September 2019.
Yes.
So most of the mobility would peak during the warmer months of the year. Is there some analysis you did with weather as a variable?
That's a great point. So for weather, right now on Purdue campus, you will not see scooters because they have been, put away because, the road condition doesn't allow you to use them. Right. So in the survey, you can consider that because we surveyed Indianapolis residents and the survey happened around September. So that is kind of their assumption in the mind, right? So they do know the weather, but they're not specifically thinking about a winter day. Okay, right. But so you can consider this as an average use, right? But on day-to-day and the seasonal variation, that's a great point. So right now you can consider our model as a, one average day model. Okay. Right. Next step would be, make it a year-long model to represent that, seasonality and the fluctuation of, you don't always have all these choices. Right. Yeah.
Yeah, this is currently assuming that given you can actually take the bike, what would the pattern be?
Exactly. So we're assessing, under what scenario they are actually, competitive with the existing modes. Yes.
It's like the app. Do you also look at what people's personal preferences are, versus bus, scooter, bike? Because I know personally, when I'm down, whatever, I'd much rather take a bike because I just don't like buses. It's sit next to,
right.
Mystery liquids,
Yes. So that is captured in the mode choice survey, right? We give them different options and say, well, given this trip in downtown, which mode you would take, right? And then that will create into, utility functions. So every single household or every traveler have their own utility function based on their social demographic information. So that is considered. Okay, slightly a little bit different. So we try to be representative in terms of our survey participants to capture, a representative sample with, car drivers, transit users, etc. So that should have been reflected. Yeah. Other questions? All right. Okay. So now we confirm that intensify the current strategy doesn't work. So how about let's put the all the bikes and the scooters and the ride-hailing cars outside. Okay. So here you can see we do reduce the share of car trips. But where did they go? They all go to ride hailing. Okay, so what happens is we actually reduce the waiting time for ride hailing vehicles, which is a very significant factor when people choose to use Uber or Lyft type of service. Okay, so that made ride hailing very desirable. So a lot of the trips actually shift to ride hailing, but as we have seen, because of the deadheading, they're not necessarily helping reducing the emissions. And by the way, we're assuming that right now we're applying the same strategy for all the shared mobility options. Okay. Okay, and then for the transit-oriented development, okay, so you can see we have a little bit higher than the previous one for car trip, but still better than the intensified, the first scenario. And we do have actually more trip going into multimodal system. So distributing these bikes and scooters along the bike line, along the bus lines near the bus stops, and also allow the vehicles to wait near bus stops for picking up passengers actually do increase the use of multimodal. So right now, this seems to be the most promising approach. Yeah, but no, this is still preliminary, right? It's very simple. What if it's this scenario? There's a lot of opportunity to optimize the infrastructure development in the system, right? Each mode may have different strategies, right? And we can have different combinations of different modes put together to improve the system performance. So we're still working on identifying the optimal development policy, and also the not just where they are, and also there's a pricing strategy we can change as well, right? And there's also a fleet sizing, right? How many vehicles do we need? How many bikes? How many scooters? How many Uber Lyft type of a service do we need? And what is the trade-off among them? And what is the relationship between pricing and the fleet size as well? So there's a, the model have a lot of potential to do a lot more exploration to answer these questions. So if you're interested in this type of questions, I'm very happy to collaborate. All right. So based on the results we have now, it's shared mobility provides a sustainable mobility, right? The key takeaway is that we need shared mobility to help us reduce car trips. That's the key. But the current way of deploying the shared mobility infrastructure and the vehicles are not helping reducing car trips, and therefore not reducing the emissions. And we do need to consider these complex interactions among different modes to help inform how do we develop this type of a system. All right, so that's about the shared mobility. So I have a little bit time that I also want to spend on give you a brief overview of what we have done in some of the other areas. Okay, so for ride sharing or ride pooling, right? Right now, if we look at the average vehicle occupancy rate, it's only 1.6 in the US. Okay, but on average passenger vehicle, we have 5 seats. So there's a lot of potential to put more people into the same car. So we have done some analysis in terms of looking at the potential to reduce emissions through ride pooling using New York City as a case study to look at if we're using traditional vehicles, traditional shared vehicles, how much emission we can reduce, how much vehicle we use. What if it's shared autonomous vehicles, okay? And do we actually find out that we may increase some equity related issues, because when we optimize the system with the shared mobility, right, the vehicles go to where are the more trips. So there are certain areas in the city actually are left out underserved. So we needed to make sure our algorithm avoid those situations. Okay? And we also considered, people may have different preference. Some people may be, I'm very environmentally conscious, right? I would only take an Uber if I can have the Uber pool option. Otherwise, I will not. Right? Some people may feel, well, I don't care, whatever is the cheapest or the fastest, I will choose that. Right? Some people may feel like, okay, I would prefer not to share, right? So we considered a different range of people preference in our model as well. If you're interested, I can share the paper here with you. Okay. Right, electric vehicles, autonomous vehicles, as I mentioned, is also in rapid development, right? Autonomous vehicles potentially could be shared electric autonomous vehicles, or could also be privately owned vehicles. We have also done some work exploring the ownership adoption of autonomous vehicles, comparing if we have a community, what if everybody buy their own autonomous vehicle if it's a desirable choice based on some adoption curve, versus the community have a shared fleet that will operate and serve the entire community. What are the differences? Okay. And then we also have electric vehicles that have no tailpipe emissions. But now, after learning, the life cycle assessment framework from the bike share example, right? That no tailpipe emission doesn't mean it's zero emission, right? We need to think about the vehicle manufacturing and also what electricity is used to charge the vehicle as well. So we have also done some work looking at what is the optimal electric vehicle battery size, and where should we build charging stations for electric vehicles as well. Now, there's one thing that we haven't looked into, we haven't talked about so far, is all these things aren't happening in parallel, right? And they could have different combinations. So our different development pathways may actually lead to different infrastructure development needs. So for example, if we want to site our charging stations, right? For autonomous vehicles, if the vehicle is just a traditional electric vehicles, right, we may consider they need to be charged at home or charged at trip destination, okay, where they park. However, if the vehicle is autonomous and they can drive themselves, right, this constraint can be relaxed, right? Because you can send the vehicle, say, well, go down the road, charge, and come back when you're ready, right? Then where do we need the charging station could be different, right? Okay. And also, if we have shared autonomous vehicles, we may only need a smaller fleet. And then if we have ride sharing, ride pooling, which means when we put more people into the vehicle, right, we're actually taking the charging opportunity away, because if we're chaining the trip from different people, right, the parking time of the vehicle will be less, right? So when the vehicle is available to charge, is also different, okay? And also, these things are also linked, because when the vehicle is at charging station, they're not available to be used by the owner or by the shared community either, right? So we have also done some work in terms of looking at different development pathways. Let's say if we have a traditional fleet, right, no sharing, no autonomous vehicle, but just the increasing EV adoption, versus a scenario that, okay, a shared autonomous vehicle, so the vehicle will become shared first, right, and then slowly become electric vehicle, or they could be, become electric first and then become autonomous, right? So there could be different pathways when these technologies start to merge together. So we have also built a model to look into where should we build charging stations in this case. So in today's talk, I don't have time to get into the details of the model, but the quick glance of the results is that the charging infrastructure needs will be very different. So it's important to consider the integration of the different technologies. All right, so the research I presented today is mainly done by my PhD student Luo Zhaoyu and Mustafa. And here I also want to thank my collaborator, Professor Brita, and her student Ricardo. And the research is sponsored by INDOT through the JTRP program. So with that, I'm going to thank you and open to your questions. Yes. Yeah.
Can you please go back to the very beginning, showing like the lifetime emissions of?
Sure. This one?
No, there was a chart like manufacturing and
This one?
please go there.
This one?
Not maybe 3 or 4. Like comparing, like, yeah, this one.
Okay.
So, is it considered like, the like manufacturing or constructing the stations? That is like just one time or first time investment.
So we have assumed the lifetime of 10 years for the stations. Yeah, for the bike share stations.
So every 10 years it is required to construct a new station.
Right, you needed to, yes. So which is a great point. So we did this study about 2017. So at that time, none of the station is older than 10 years. So we got this 10-year lifetime from interviewing the system operators, and they got this number from their suppliers. Right now, there's also actually a couple of stations that just goes beyond 10 years. So we plan to, kind of go back, talk to them, say, hey, how does the stations doing right now? Is 10 years still a good number to use?
It is very interesting that I just thought that if we just like convert to some kind of sharing each transportations and bikes, like reduce the total like carbon emissions, but this is a like different way of representing, because yeah, there's been many contributors, because we are going to like have very like eco-friendly with using some sharing bikes, but this is not exactly that.
Right, so it's really depending on, without that shared bike, what were you doing like before, right? If you were driving and now you switch, yes, that will definitely reduce your emission, right? If you were walking but now you switch your bike, it improve your mobility in terms of reduce your travel time, but you actually increase your emission. Yeah. Yes.
So that's why shared e-scooters so high, is because so many people, they're not ditching the car for the scooter, they're ditching walking for the scooter. So it's basically just a whole nother emission problem.
So there are two things, right? Here, what we show is the emission factor of the mode, right? So that is regardless of what mode you're replacing. Okay. So the e-scooter is very high here is because they have very short lifespan. So they actually broke very rapidly and have to be replaced. So there was an article talking about e-scooters in Indianapolis. Average lifetime was only about a couple months when they first been deployed. Okay, and now they actually improved the scooters. Now they last longer.
Yeah.
So a lot of that was from the you have to keep putting new scooters, and also through the rebalancing, scooters needs to be rebalanced as well. Yeah.
So do you think it'd be worth banning shared scooters and encouraging more people to just buy their own, to take better care of them? Don't need to rebalance them. Do you think maybe that's a policy?
Well,
Good idea.
I think, you can be, it's possible to incentivize people to switch to, personal scooters. But, from the other side is also, we have bikes, personal bikes available for a long time.
Yeah.
But, why would people prefer to use, share the bikes, share the scooters? There's this convenience side of things that, I don't need to worry about it. I don't need to find, have to, think about, oh, what if my bike or scooter is stolen or something, right? So there is some benefits of the shared infrastructure, right? But if everybody take our personal bike, we have a much lower emission.
Yeah.
Yes. So providing the sharing infrastructure actually generate a non-trivial emission.
Yeah.
Yes.
So it's pretty interesting. You mentioned this earlier, but it seems like if I was an e-scooter or e-bike company, I would want to place everything downtown because that's where the majority of people are. The short trips are good for me, right? Because
Yes.
usually it's like a fixed fee plus X amount per mile. So from a profitability standpoint, it's better for them to put it downtown. But from a carbon emission standpoint, it's better for them to be outside. So how do you marry the two? What kind of policy or incentives from the government maybe are we going to have to see for this to become reality?
That's a very good point, right? That's exactly what's happening right now is, if you're a scooter business, right, you would want to put where the most of people are, so people use it. But keep in mind that all those are short trip, right? So you're actually making less money out of each trip, right? If you put the scooters in locations where there are longer trip, potentially you could gain more money from each trip, right? But we do need some incentive from the government or some policy regulation in place. For example, guarantee a certain number of scooters. So some city have this rule. You have to make sure you have a certain number of scooters in certain regions. But a lot of the cases, the cap is just, well, I think, you need to put 100 scooters there, right? It's not backed by this type of analysis, but our model can actually provide some technology knowledge support in terms of, okay, it would be benefit if we have, this many scooters here, this many scooters here. And also every city have a cap in terms of, how many bikes or scooters the operator can deploy. And very likely, in many cases, that number is also, simply based on, per capita. That city used, on average per capita, this many bikes, we are going to use the same number, right? So potentially how we design the system can be much more informed by the data we currently have, right? But, a lot of those was because these things just new, right? The scooters and bikes just showed up and the city doesn't know what to do with them, right? But now we have started to have the data that we can analyze through their existing use. We can then use that information to improve the further development of the system. Yes.
I'm curious about, I know this project is founded by Indiana Beauty, so it's focusing in the area. I'm just curious about the demographic factor, whether we will see different pattern if, say, this whole thing is deployed in San Francisco or in a city in Vermont or West Virginia, whether, the demographic will play a big role in this besides weather.
In terms of shared mobility use. Yes, so we are exploring that. So we actually have collected data for about 800 different systems globally. So we want to compare in terms of, what are the patterns beyond, the built environment, about the built environment, the people in terms of, where people use more, where does it make more sense for us to deploy this system? Because it's also very expensive to just deploy and try it out and find out, okay, it failed, and then, move the bike or scooter away or kind of throw them away, right? If we could have a screening model to analyze, oh, this is likely to be a place that's suitable for shared mobility, then it can have a lot of value. So we're working on that. Yeah.
Hey, no more questions. Let's thank the speaker. Feel free to ask questions offline, keep questions high, and Next, we were gonna have Professor Chi Zhu from Northwestern University, and he's gonna talk about separate critical systems and design automation. Thank you for coming.
Oh, yeah.